Now we'll learn more about Dynamo. In this case, we use a definition, and then we'll explain the phrases inside the definition. These instructions will tell the computer a series of steps to follow. It's a simple process which consists of a few steps. For example, if you would like to create a swan origami, just follow the instructions to arrive at the final result and obtain a nice origami. The same can be said in the case of instructions that we give to a computer. When we establish those instructions, we don't need to repeat them over and over again because the computer already knows what to do. Thus, the design process can be improved by specifying the decisions to be made using a programming language. Our goal, in addition to documenting the result, is to create steps to reach that result. Next, we're going to analyze the advantages that the computational design implies when we apply it to architecture, engineering, or other related professions. In this case, we're going to explore multiple design options, starting from an already created process, just changing some of them, the parameters, we can obtain different results. Another advantage is the ability to transfer, edit, and analyze data from one application to another, even though certain data may not be available in the same application, because software companies would like us to do everything with their programs. The truth is that our work is so complex that it requires the use of many tools. So when it comes into contact with the data, we should be able to export it to other applications to complete our tasks. We can also automate repetitive tasks and finally simulate the performance of the building. We don't have to wait until something is built to know how it will behave, since we could use computational design tools to simulate the performance. Let's review the second part of the definition of principle. They are nothing more than a series of instructions. In this case, we use graphical elements instead of making textual specifications. These elements are usually interconnected nodes. When we talk about programming, we use a series of codes written in a textual form. Let's observe the following example of on-screen code with variables x are shown, then y ratio. We create a point called myPoint, which represents the point in x and y. Then we create a circle using the data of x and y as the point and the radius. It is a series of instructions that we have given to arrive at a final result. The following example consists of doing the same of graphical form. We have a document in which we do the same thing. Let's observe the value of x, one of y, and one for the radius. Next, we create my point, which will be the center. The radius will be the one we define, and when we execute it, we observe that it shows a circle. Note that these two programming environments do the same thing, one in textual form and another in graphic mode. The big difference is that when we do it in a visual programming environment, instead of using lines of written code, we use the nodes that are connected with each other. This is the great advantage that Dynamo represents because we have the option to create computational designs by doing it visually. Everything on a platform that is specifically created to support us in the design of architecture and engineering. Dynamo is a tailor-made tool. In upcoming classes, we will begin to familiarize ourselves with the programming environment. Let's check the user interface now. Once opened our Dynamo executable, we proceed to create a new file. On this occasion, we found a fairly well-known interface with respect to other types of programs, where in the superior part, you'll find a menu bar. And a toolbar on the left side, perhaps what you're most interested in, a panel called Library. In the latter, we can perform various code search. For example, here we could search for point. Typing point, it will give us several options to create those points. Leaving the mouse placed in one of these options gives a description of the right, and when we click, we can create that node. Another way to explore the library is by doing it manually. Note that there are 7 programming sections and 1 extra section of Revit. Here we go to Geometry, then look for a circle and choose one of the internal nodes. Once selected, we can add it by clicking. On the right of our surface, we find the workspace. Notice that it works by cards, and we can create several cards for several files. Importantly, our workspace is made up of 2 modulities of visuals. The first modulity is the one that allows us to edit the nodes. However, we cannot change the geometry. If we zoom in or out with these buttons, even so, you wouldn't be zooming in or out of the geometry in the background. To be able to edit the display of geometry, we have to change the display mode. We do that by using these buttons that are in the upper right part. Notice that the graph view is now active. By clicking this other button, we activate the 3D view. From this, the nodes have become transparent and use the keys to zoom in or out. To change from editing mode to the other more quickly, we can compress the Ctrl-V keys. Note that we can use this option, Adjust in Window, so the program shows more closely everything that exists in the window. But if you use the scroll mouse, we could do the same, and this also happens when we're in geometry. We can move in or out and zoom to fit or adjust the window. Also, if we have one node selected, we can click on the Adjust window and just adjust the nodes we have selected. We can make pan using the framing tool and doing click to drag, but we can also make pan simply by pressing the middle mouse button. If we are in geometry and press the right click of the mouse, we can make a rotation. Now, if we are in the view of the graph and right click, we will display this menu where we can choose various options. No matter where you click on the workspace, you can also type, let's say, by coordinates. Which works just like the search command we mentioned in the library. This way, we can choose a node, click, and place it. These are some of the basic tools we need to know our interface. Later on, we'll see some other tools within the menus. For now, this will be enough to start working. The nodes will serve as blocks to build our programs. So let's take a closer look at them to learn how they work. We already saw in the kind of interface that we could look for it through the different categories of the library. We could also search on the search bar by name, but perhaps the quickest way to do it is by right-clicking on the workspace and typing the same name of the node. By coordinates, since we'll choose this node to use as an example. We observe that in the upper part of the node is its name. First, the name of the category separated by a period, then the proper name of the node. When we place the mouse over it, it also specifies how it works and when it does. But by doing double click on the name bar, we can place a custom name. In addition, we can observe that within each node there are ports, some to enter data and others to extract them. If we place the mouse on some port, it'll tell us the type of value it receives and what is the amount it has placed by default. For example, X and Z accept a double value, which means a number with decimals, and its default value in 0 in X and Y in Z. That's why, although we haven't entered any data in this mode yet, it's already creating a point. As you can see here in the 3D graph, a point right at the origin. If we right-click on the inside of the node or its body, we'll have some options like eliminating it, select the type of socket, and preview, which we'll see later. Also, if you place the mouse over the node, we'll see at the bottom the description of it. And if you click more on the description, you'll see what's going on, the type of data it handles or from which it's extracted. When you remove the mouse, it disappears. If we want the data to remain visible, we must go to a border, go down, and then press the button with the pin icon. In this way, the data extracted from the node will always remain visible. If we want to make it invisible, we just have to press the same pin again. Now let's see how we can create a duplicate node. We could do this by selecting it and pressing the Control key, and then dragging it towards one side. We could also select a node, go to Edit, copy, and then edit text, or we could use a keyboard shortcut. Select the node, press Control C, and then Control V to paste it. All of these methods are valid. As we can see, we can drag it, selecting it from some point, then moving the mouse, and we could erase them by selecting several nodes and pressing the Delete key, or by right-clicking on it and clicking on Delete. Let's create a different node and see how we can connect it. To do this, we'll do a new search, number, and select the option number slider. This value of the number can be connected through of its ports with the following, for which we must click on the exit port, and then on the port of entry, and it could also be the other way around. We might even be able to change position on some connection, saying that instead of going to Y, go to Z, and clicking first on Y and then on Z. If we delete a connection, click on the final port and then on the workspace, or on the initial port and on the workspace, canceling the operation. We can create several connections from the same port to subsequent ports. Note that at this moment the value of the slider is 1, and so the point is no longer in the origin, but that is a little shifted with X and Y equals to 1. Now let's see how it can work. As you move the value of the slider, the point is moving on a dynamic way. This happens because the auto option is on, so it runs the code automatically. There are different states within the nodes. For example, if we right-click on a node and press Lock, it is placed below transparent color, and besides, that has a dotted gray line around it. It is important to know that when a node is blocked, even if we try to move the input data, the node is still the same place, which implies that the data you had at the time you blocked it will remain the same. If you want to see it again, click on the node and press again the lock option, thus releasing the result, so that if we move the slider, it will also change the value. In the same way, we could do right-click and disable the preview option. This does not lock the value of the node, but instead deactivates the execution of the same. This means that it is no longer being taken into account, and it takes a blue tone. This option can be useful if we are testing different programming options. And although we don't want to delete the node, we don't need it to be executed. If we want to go back to activate it, right-click and activate the preview. As a final point, sometimes the nodes are disorganized. For example, we'll make a copy of this node that also has some connections, and now we'll see how we can keep everything organized. If we move them and then have them disorganized, or for some other reason they're not visible as we want them to be, we can go to Edit and use the option Presentation of Cleaning Node. Or we can access this option by pressing the Control and L keys. In this way, the node we have selected will be ordered, but if we have selected any node, it puts them in order. This is quite useful, especially when we create more complex programs. Finally, we can observe that the connectors are made with curved lines, though we could use straight lines. To change that option, we can go to the menu View, Connectors, Connector Types, and select Polyline so the connections will be straight. In this case, we will leave it in Connectors, Connector Type, Curve. With this data, we can already do a lot inside a Dynamo. In the next class, we'll see a practical example of how you can use the knowledge acquired so far to solve a problem. In this class, we'll see a practical example of how we can use the knowledge required so far to do something fascinating. We'll create a circle to which we'll be able to change its size dynamically using a central point and external point that'll define its radius. And finally, we'll see how we can create several circles simultaneously. If we want to create a circle, right-click, type the word circle on the keyboard, and we notice that presents us with several options. However, we will select the first by center point radius, which requests to create the circle, a central point and a defined radius, which is a distance. The central point is a type of point that is the entry data, while the radius is the type of double, so we're going to create 2 points, one that defines the center and another that defines the distance to the outside. To do this, right-click on the workspace and type by coordinates. From the result, we can choose the option by coordinates x, y, z, which corresponds to creating a point by coordinates x, y, and z. We create a copy with Control-C and Control-V. In the case of the first point, we want the values to be static, so only add 2 numbers, right-click again and type number. We duplicate it, and now we join them to x and y, so that now this point is in the origin. Secondly, we would like this other point to be dynamic rather than static. So let's add a number. For this time, we'll choose number slider so we can change it graphically. We connect this last one with the first point, and we're going to create another slider to connect it with the second one. Since we have these 2 points, we must establish distance between them. If we go to the graphics view and press Ctrl-V, there it created those 2 points, one in the center and one at the end. Now we'd like to verify the distance between them to find the relationship with the radius. To do that, we have a node, so we type distance, and we'll notice that there's a node called distance 2, which gives the distance between 2 geometries. The geometry would be the first point and the second point, so this way this node is calculating the distance between the 2 points. If we connect that distance to the radius, we force the circle to have a radius exactly equal to the distance between them. If the central point is this point, we would change these values in the circle and move from its center. But we wouldn't necessarily want the radius to be exactly the distance between the points. It could be another relation, so let's momentarily erase this connection to see something more interesting. If we double click on an empty space in the workspace, then we can create a block code. That, when we look closely, we notice that allows us to write our options. For example, let's say we would divide a number x and another y. We must place x over y and end with a semicolon. Note that the block identifies that x and y are variables, so we must introduce them. Let's say we want to divide x, which is the distance between a number y, which we will define by adding another slider, whose value will be 17, and we assign it to y. In this way, this code will divide that distance by the 2 points by 17. While if we connect this to the radius, we notice that it is much smaller. The radius is 17 times smaller than the distance between the points. Thus, we can see how we can go further in complexity. If you want to keep the code in order, simply after selecting any node, press the keys Ctrl-L and you'll get it more organized. Now, let's see how we can create several circles simultaneously. Suppose that instead of using only 2 numbers, we want to use a sequence of numbers for x and y. So let's disconnect these cables or connectors and create a new node called sequence, identified in the program as sequence as well. Note that the sequence needs a number to start, the number of numbers we want, and what step there is between each number. We'll start from 0. We want 10 numbers, so we connect it in quantity, and we're going to create a new number that's, say, the steps. In this case, we'll make it move 2 by 2. Now, resting on the edge that unfolds lower right and place the mouse on it, we can see it creates 10 numbers from 0 to 18 in pairs. That sequence, we will join it with the values of x, and at this point, we can see how it has created many circles. We're also going to link it to the y values, so that the center will be the x and y, which grows in pairs. If we go where it says sequence, we can see that it is creating list numbers, but where it says points not by coordinates, when you click on the pen, we'll see all the points we're creating that are 10. However, by right-clicking and selecting that the socket is a vector product, that is to say not to create 10, but from 10 to 10, we notice how it has created a grid. If we place the mouse and go down, we'll see it's creating a list of vector products. The socket function is used for this. In this case, the ratios are very big, and that's why it's not working. But now we're going to increase the relation to 17. If we select it, we'll be able to see as each one of those has been growing from this point onward. Note that as the radius is defined to the distance of this point moves, so will the radius of the surrounding circles. For example, if you move the slider to move the point, notice how they are changing the radius to measure that the point moves, both in x and y. A trick could be if we select all the circles by clicking on this node and go into the graphics view, pressing fit in the window. Then we'll adjust in the window only the circles we're seeing. Let's rotate it to see them better. Also, in the visual window, we could select this point and use the track for movement to make on our own. Notice that when you move them, it changes the radius of the circles around it, just pressing the dot and dragging it. It's not complicated. If we want to keep the code tidy, we can press Ctrl L again, having selected everything. This way, we have seen how simply a node, although it says to create a point, it can create several if there are multiple entries. Perhaps one important thing to remember is that we can use the lace to change the way the data we are entering will be handled internally. We can faster, making only one line. We can do it as a vector product, or the third option is longer. When we talk about the lists, we'll study in more depth the lace option. For now, it's enough to see something practical with what you've learned.